back from Thanksgiving. Just 4 more days of class. Okay, 2 this week, 2 next week, then it's finals week. We do have our final kind of late, and I cannot change that. I believe it's Friday of finals week. At least it's early in the morning. I mean, that's not good in that you have to get up early, but it is good in that you get done as quick as possible and can get out of here and get going home as soon as possible. But yeah, I can't change the final exam time. That's set in stone. What are we going to do today? Lecture 24. Part A, we're going to review chi-square test, linear regression model, and regression standard error. And this last one we really haven't focused on a whole lot. So we will get into more detail on that. With the chi-square stuff, I'm going to go really fast. If you were not here a week ago, before Thanksgiving for that, you probably should watch it on YouTube to try to get the idea more slowly, because again, I'm going to go pretty quick with the ideas and formulas, so that we can do it in half an hour here before the quiz. In lecture B, we're going to get into more detail about regression. We're going to talk about confidence intervals and hypothesis tests on a population slope. You'd like to estimate a population slope, and we'll talk about how to do that both with spreadsheets and with a formula. Alright, so let's look at the chi-square test. We're going to start with, first of all, just glancing at the formulas that we looked at last time. Let's see. You have, here was the situation with the example we considered last time. We were talking about meal preferences for males and females. Do they prefer home cooked or takeout or a restaurant on a Friday night? These were the actual data values from the sample. 8 out of 10, 16 men preferred home cooked, 3 out of 16 men preferred takeout, 5 out of 16 preferred restaurant, etc. 4 out of 17 women preferred home cooked, 7 out of 17 takeout, and 6 out of 17 restaurant. And we're wondering, we've got essentially an explanatory and response variable here. We're wondering if the person's sex, male or female, determines their meal preference, home cooked, takeout, or restaurant. This is the explanatory variable, this is the response variable, and they're both categorical in this case instead of quantitative, though we do have numbers involved. We've got counts, how many people in each kind of category. And we can calculate proportions, for example, 8 out of 16, 0.5 or 50% of the men prefer home cooked. Alright, so that's the actual data. We're wondering, is there a relationship between these two categorical variables or not? We're going to do a hypothesis test. The null hypothesis is going to be that there's no relationship. Oftentimes the null hypothesis in a general kind of statement is there's no effect or no relationship between variables. And that's the case. There's no relationship between the person's gender and their meal preference. The alternative hypothesis would be that there is a relationship. How do you actually do that? It's with something called the chi-square test. You have to take the information in this table and compute a new table that are called expected numbers, where you assume the null is true, you assume there's no relationship, that men and women want the same type of meals overall. How do you do that? What's the method? Well, there's a formula to find these expected counts here, right here. Take these row totals, for example, the 16, times the corresponding column total for a particular cell, like this cell. 16 times 12, those two totals, 16 and 12, go with that particular cell. It's in the same column and the same row as those two numbers. If you take 16 times 12 and divide by 33, I'm essentially using this formula, you will get about 5.818. That's the expected number of men that would prefer home cooked out of 16 men total if the proportions of men and women who prefer home cooked was the same. Don't forget the logic behind this formula. This formula kind of hides the logic. The idea is if the preferences between the men and women was the same, then the total numbers in this column would be a better reflection. Essentially, it's a pooled sample. It'd be a better reflection of the true population proportions if you assume those population proportions are equal. So, for example, for home cooked, 12 out of 33, a little bit bigger than 1/3, would be your best estimate if the null hypothesis is true for the true proportion of all the men and women who prefer home cooked out of the whole population. This is a sample. 12 out of 33, that row total divided by n would give you your best estimate for that proportion. If you now take 16, the column total for the number of men, that's the total number of men, and multiply times the fraction 12 out of 33, that would give you, if you think about it, the expected number of men who would prefer home cooked if the true proportion of men who prefer home cooked was 12 out of 33. Say that again? Catch that? I know I said it fast. Again, this is a little bit bigger than 1/3. Maybe we should figure out exactly what it is. 12 out of 33 is about 36.4%. Okay, so what we're saying again is if the true proportion of men who prefer home cooked on a Friday night is equal to 12 out of 33, about 36.4%, then if you got 16 men, you'd expect about 36.4% of them to prefer home cooked. Multiply that percentage times 16, you get about that. You can try that out. But that's the exact same thing as doing this formula. Taking 16 times 12 out of 33 is the same as doing 16 times 12 and then dividing by 33. So don't miss the logic. And if I said that too fast, you're going to want to think about it after class. Okay? Don't miss the logic behind this formula. This formula just gives you a quick method to compute the numbers in the table. Once you've got those expected counts in that expected table, then you can use this formula. It's a summation to calculate something called the chi-square statistic. That's not an x there, even though it looks like an x. It's a chi, a Greek letter chi. It's being squared. You might wonder, why is it being squared? Well, don't worry about that. It's just a symbol. Okay. Chi-squared is this summation, which does involve some squares. For each cell in each table, take the observed count minus the corresponding expected count. Square that number and divide by that corresponding expected count. Do that for each one of those blue cells in the main body of the table. Add those numbers up and get the value of this chi-square statistic. The calculation here definitely can be kind of long and painful. Okay? You can use your calculator and spreadsheet on homework to help you here. We're now going to do an example where we use this formula. Once we have the statistic, what's the big idea? We're trying to test the null hypothesis that there's no relationship between the variables. If the chi-square statistic is extreme, that's going to lead to a small p-value, which will lead to strong evidence against that null hypothesis, as usual. Okay? Extreme test statistic values give you small p-values and lead you to rejecting the null. It gives you strong evidence against the null. We're going to have to deal with the degrees of freedom as well. It's going to be the number of rows minus 1 times the number of cells columns minus 1. R times C is the number of rows times the number of columns in the main body of the table. The blue cells we're focused on. This one has 3 rows and 2 columns. Ignore the totals, column and row. 3 rows and 2 columns for that one. So R is 3, C is 2. R minus 1 would be 2, C minus 1 would be 1, 2 times 1 is 2. We will see that that will be the degrees of freedom. Let's do a new example, actually. Here's a new example. Okay? Actually, this is going to be one of your homework problems. Maybe not for a future class, but for you guys, this is going to be one of your homework problems. And another example we're going to do is going to be one of your homework problems, too. Okay, so you should try these on your own before next time without looking at the video. Do your best to try these on your own. But we'll go through them now. A survey of 656 boys and girls who are 13 to 18 years old asked about adequate sleep and other health-related behaviors. The recommended amount of sleep is 6 to 8 hours per night. I'm trusting that that's right. In the survey, 54% of the respondents reported that they got less than this amount of sleep on school nights. Also, an exercise scale was developed and used to classify the students who were above or below the median in this domain, meaning above or below the average, the median amount of exercise. Here's a 2x2 table with counts of students classified as getting or not getting enough sleep. There we go. So you've got a group of students, a bunch of boys and girls. Some exercises more than the median hours per week. Some exercise less than the median hours per week. Some say yes, they get enough sleep. Some say no, they don't get enough sleep. This is not really a well-designed experiment because you're trusting what they're telling you, I suppose. All right, well, let's just go ahead and go with this. those are the two categorical variables. Amount of exercise is the explanatory variable. It's horizontal, like X. Amount of sleep is the response variable. It's vertical, like Y. We're wondering, are these related or not? The null hypothesis would be, when I'm not going to take the time to write it down, would be that there's no relationship. Knowing whether a kid gets high exercise or low exercise does not affect your prediction about whether they get enough sleep or not. Now, with the sample data, there is a definite difference, right? Take a look at these numbers. 151, 148, those are pretty close together. It seems for people who would get high exercise, the percentage who get enough sleep or who claim to get enough sleep is pretty close together. Pretty close to 50% in both cases. On the other hand, for people who say they have low exercise, definitely a fairly large proportion of them are not getting enough sleep. So on the surface here, it does seem like there is a difference. It seems like we're probably going to reject the null hypothesis. It seems like knowing whether they exercise a lot or not does affect your prediction about whether they get enough sleep or not. We're probably going to reject the null, but you actually have to carry out the test to make sure. How do you carry out the test? Well, again, find these totals. Let's go ahead and fill them in here. You're going to have to do this. Total across the rows, first of all. 151 plus 115, that's 266. That's the people who said, yes, we got enough sleep, whether they exercise more or less or not. Total across the next row, 148 plus 242 will be 390. You can also total down the columns, 151 plus 148, that will be 299 people who said that they got above the median in exercise. And then finally, low exercise, add those up, you get 357. And how many people total, how many boys and girls total? You can either add up across this row or down that column. You should get the same answer either way. And the answer would be 656, either way you do it. And that matches 656 boys and girls up there. So that helps you fill in the rest of the actual data table. Let's now make an expected table. And for sake of time, I will abbreviate ES for enough sleep, HE for high exercise, LE for low exercise, T for total, Y for yes, N for no. Okay, use that formula, row total times column total divided by n for each one of these cells in the middle here to get the expected counts. Okay, get your calculator out. Go ahead and make this bigger. Take a look at the numbers in this table. Okay, so for example, for the people in the high exercise category who say they get enough sleep, first row, first column, take the row total for that row, and the column total, or excuse me, the column total for that column, the row total for that row, multiply them, 299 times 266, and then divide by n, 656. Carry more decimal places than I did in the other slide. Let's go ahead and write all those in there. 121.2408537. 121.2408537. That would be the expected count that goes there. Okay, you can go ahead and work on the other ones. I will as well. I guess you can listen to me if you prefer. For the next number in that same row, take 357 times 266 divided by 656. 144.7591463. You should be checking my answers. If you get a different answer and you're pretty sure you're right, let me know. There's a fair amount of work to do with this stuff. I think we're going to have to somehow cut this example short to a certain degree. What about the lower left one? Take, that's corresponding to this cell, take that row total times, this column total times this row total, 299 times 390 divided by 656. 299 times 390 divided by 656. 177.7591463. And finally, one more here. For that one, it's in the second column, take the 357. It's also in the second row, take the 390. 357 times 390 divided by 656. 212.2408537. Did it look good to everybody? Anybody tracking along with me, checking my answers? Once again, that's just a mechanical way of getting these answers. You should not forget what it means, okay? And probably, not necessarily on today's quiz, but maybe on the test, the final exam, I might test you on what it means. Again, you should understand that, for example, take this very last one that we just did, that corresponds to that cell. 390 out of 656 would be your best estimate for the true proportion in the population of those who say they don't get enough sleep, whether or not they exercise or not, a high or low amount. 390 divided by 656, about 59.5%. Not sure where the book is getting 54%. There. So we can kind of ignore that. 390 out of 656, about 59.5% would be your best estimate for the proportion of the population that doesn't get enough sleep. If whether they exercise a high or low amount has no effect. You're pooling those two samples together, essentially. If you multiply that percentage by the total number of people who say they exercise a low amount, below the median, that will give you the expected number of people. That's 59.5% of 357, about 212 people. But we go ahead and use more decimals to hopefully not have our errors build up. We only round at the end. Okay, that's a fair amount of work, and we're not done. We still have to use that formula for the chi-square random variable. The statistic, right? Right there. We haven't done that yet. Ugh. How can I save some time here? Well, remember, I was trying to do chi-square stuff on Google Spreadsheets, but it wasn't working. But it does work on Excel, at least if you use the built-in functions. The arithmetic can be done on either one to calculate the value of chi-squared. Let me go ahead and just fill in these numbers here. And for the sake of typing time, I will round, even though I probably shouldn't, 121.24085. I'm looking up at the board here as I type. 144.75915. Now look here, 177.75915. These are the expected numbers, and then 212.24085. Okay, we got 4 terms in the sum. Okay, Let's put it over here. What's the first term? The formula was to do the summation, I'll abbreviate, of observed values minus expected values squared divided by the expected values. I'll use O for observed values and E for expected values. So for each corresponding cell, take the observed value. For the first cell, it's in cell C7, so the observed value is 151. Subtract the corresponding expected value over here in cell H7. Square that, and then divide by the expected value. You see that? Zoom in on that, maybe? It's kind of dim. C7 minus H7, observed value minus expected value squared divided by the expected value. That will be the first term in the chi-squared cell. What's the second term? Go to, say, this cell. Keep zooming in here. D7 minus corresponding expected values I7 squared divided by I7. I think we'll make this bigger here. It's not working. I zoom in now. Oh, that's because I was thinking I was on sheets. Zoom. I'm used to a Mac, and so I can't find my zoom here. Anybody see a zoom view, maybe? Here we go. Zoom. Do the next one, the lower left. Observed value, right there, minus expected value right over there. Square that, divide by the expected value. One more. This number minus this number squared divided by this number over here on the right. Continuing to use that formula there. Now add these up, you get the value of chi-square. It's a pretty big chi-square value here. Pretty extreme, 22.6 approximately. I'm betting the p-value is going to be pretty small. If you want to use the table now, zoom in on this too. How many rows and columns were there for that table, the main part of the table? 2 and 2. It's 2 by 2. 2 values for the exercise level and 2 values for the sleep level. So R was 2, C was 2, therefore R minus 1 and C minus 1 are both 1. The degrees of freedom is 1. That's the way degrees of freedom works in the chi-square context with these tables. 1 degree of freedom is right up there. Our chi-square value is real large. What was it again? I forgot. 22 or something? It's off the chart. The biggest number there is a 12.12. So it's to the right of that. What does that tell you? Well, this number right there, that 0.0005, is a p-value that would correspond to 12.12. It's the area to the right of a chi-square distribution with 1 degree of freedom. To the right of 12.12 is 0.0005. Our numbers further to the right, our p-value is even smaller. Our area is even smaller. So you can report the p-value is definitely very small, less than 0.0005. We definitely have strong evidence against the null, like we expected. Okay, it does seem like the exercise amount effects is related to the amount of sleep. People who exercise more seem to get better sleep, was the conclusion if you look at the data. Can we get a more precise chi-square value? Yes, I actually typed in the wrong function last Tuesday that I was planning to type in. You can either do chi-dist or chi-test. I actually meant to do CHITEST, but I did CHIDIST by accident, okay? And that was why it didn't quite work the way I expected. If you want to do CHITEST, it says actual range, comma, expected range there. Highlight the actual values, then put a comma, then highlight the expected values. We will get a p-value for this test. It's going to be very small. I'm sure it'll be in scientific notation. 2.01883, e negative 6. That means 2.01883 times 10 to the negative 6, which means 0.00002018883. Very small p-value. Definitely reject the null. Once you got the value of chi-square, you can use the other one as well. I forgot. Okay, CHIDIST. Type in the chi-square value that we got. What was it? 22.577. Type in the degrees of freedom, which was 1. This should be the same number. Yep, close. Okay, I rounded a little bit, so. Probably the first one's more accurate, but I mean, it's such a small p-value anyway, it's not really a big deal. I mean, we really should round these p-values to 0.00002. Okay. All right, that's a quick summary of what you should know about chi-square. I am going to give you a problem, and you can certainly use your technology to help you do the calculations, whether it's just your calculator or a spreadsheet. I'm going to give you a problem that is going to be more complicated than that, besides that one problem. I'm going to give you this problem as well, and I don't have time to go over it. The method is the same. What is RDC? Remote deposit capture. Evidently, it's a method that people can use to deposit their checks more quickly, I guess. They just take they scan it. And that's good enough. Talking about scanning checks there. Okay. We're looking at banks and whether they offer remote deposit capture. Some do, some don't. By region, we're wondering, are these variables related? Whether they offer remote deposit capture or not, and the region. Are those two things related? So we're essentially wondering whether the distribution of these numbers as proportions out of the total are the same or not. Or really, the null hypothesis would be that they're the same, and the alternative would be that they're different, and we're looking for evidence against the null. Do we have strong enough evidence against the null? So you're going to have to total all these things, total the columns, total the rows, find the total number of banks overall, calculate the corresponding expected table, just like we did with the formula, row total times column total over n. And then you'll have to calculate the value of the chi-square statistic. So it's going to be a lot of work. The main key thing to watch for here, though, is the number of rows is no longer 2. It's 1, 2, 3, 4, 5, 6. R is 6. C is still 2. The DF is still R minus 1 times C minus 1. That, in this case, will be 5 times 1 is 5. There are 5 degrees of freedom. So you've got to use the 5 degrees of freedom line in the table. By the way, you should make sure you practice the table and not just use the technology to make sure you can do that in the test. So practice the table at least. And check it with Excel. And it does seem that you have to use Excel at the moment. It doesn't seem like Google Sheets does the chi-square stuff yet. Okay, that's going to be one of your homework problems as well. All right, for a few minutes, let's also review some things about regression before the quiz. Just for a couple minutes here. I think the main thing I want to review about regression before the quiz is just to emphasize a couple things. First of all, again, there's this abstract regression model, this big box with a bunch of crazy stuff in it. Big picture, what is this about? Actually, it's probably better explained with a picture than looking at a bunch of equations. This picture here. This is an example in the book related to how training time affects productivity. entries per hour, data entries or something. Does the amount of training time explain the how somebody does in entries per hour? Those are the two variables. This is explanatory, this is response. They're quantitative instead of categorical. You'd have a scatter plot, different amount of training time for different amount of people. This line here is sort of a three-dimensional picture of the thing, is supposed to be the population regression line, telling you that you can find the mean of all the y's for any given x by using this formula. That's an assumption that you make. Actually, it's probably not exactly right. It's a simplifying assumption that you make, that there's some line that's going to give you the mean of the y values for any given x value. There are three x values shown here. Right about there, there, and there, where you see these normal curves. The y coordinates of the point on the regression line is supposed to be the mean of the y's, the mean entries per hour for those people with that amount of training time. What is the normal curve supposed to represent? Well, for any given person who's got a certain amount of training time, say this amount, there's going to be a spread among all people who have that amount of training time. Some of them still will be faster than others. The normal curve is supposed to model that kind of spread. Sigma is supposed to be the standard deviation of that normal curve. The standard error that you read about, then you calculated on your homework, is supposed to estimate sigma. You use this formula for it. Take the square root of 1 over n minus 2 times this summation. And we've seen that summation before. These are the residuals right here, the EIs. So you're squaring those residuals and adding up those squares. This whole thing is what we've called SSE. That's summation, sum of the squares of the errors. Errors being synonymous with the residuals. S, this regression standard error, is supposed to estimate sigma, the variability, the measure of variability, the standard deviation of those normal curves in the y values for every given x value. You assume those are all the same in the model. That's a quick summary that I wanted to say right before the quiz, and now we'll take the quiz.